In this video, I'd like to address a point that I describe in my book, Freed from the Iron Grip of Frost. The topic is, how does the greenhouse effect work? How does increasing carbon dioxide in the atmosphere lead to warming of the Earth? The common view is that extra CO2 leads to extra blocking of infrared radiation from the surface of the Earth, and that causes warming. It's not as simple as that. In this video, I'll tell you how it actually works. What's really happening. Now, just to introduce the background, we all know that the atmosphere keeps the Earth warm through what we call the greenhouse effect. Visible radiation from the sun warms the Earth. Much of that solar radiation gets through to the surface, warms up the surface of the Earth, and then that warmed Earth radiates out to space in the infrared portion of the spectrum. Now, the Earth's atmosphere is made up of molecules like water vapor, carbon dioxide. These interact with infrared radiation and they scatter the radiation as it heads out into space, reducing the flow of infrared radiation from the surface of the Earth out to space. Reducing the outward flow leads to an imbalance. There's more energy coming in than going out, and that has to lead to warming. Without the atmosphere, the Earth would be about minus 18 degrees Celsius. So we gain about 33 degrees of warming by having the atmosphere. Those molecules interacting with the infrared radiation from the surface of the Earth give us an extra 33 degrees. Without that, the Earth would be largely uninhabitable. We see on the left here the solar radiation in the visible. This is what we can see with our eye. Coming in from the sun, a lot of it reaches the surface and warms the surface. The red there shows the infrared going outward. So the warmed surface, just by virtue of its temperature, gives off infrared radiation, which tries to head off into space. So the diagram shows one branch radiated directly to space from Earth. These are wavelengths where the molecules in the atmosphere do not interact with the radiation. The radiation can pass freely from the surface out to space. This branch here shows wavelengths that do interact with the molecules. We're seeing here 64% of the radiation going out is coming from clouds and the atmosphere, i.e. molecules in the atmosphere. If we look at these numbers, we can see we add them all up. 6, 24 gives us 30, 36 plus 64, 100. So that's a balance. Everything adds up to 100%. Now, this satellite image shows the Earth in the infrared, taken from a satellite using an infrared detector. We can see that in the infrared, the Earth is opaque. We can't see through the atmosphere. The radiation we're seeing is coming from levels. In this image, the whiter the shade, the higher up it is. So we have to imagine that we're looking down into the atmosphere of the Earth. We can only see a certain way down, a certain distance down, like looking into a fog. If somebody walks away from us into fog, there comes a point where they're no longer visible. That's the radiating level. So at each point on the Earth's surface, there's a level in the atmosphere where the infrared radiation is escaping to space, where the atmosphere above it is clear enough in the infrared that the radiation can get away out to space. Now, the other point is that the higher up in the atmosphere, the cooler it is. In Earth's atmosphere, the higher up you go, the cooler it gets. and the weaker it gets, the weaker the radiation gets. So higher up in the atmosphere, it's cooler, weaker radiation. This will be, as we'll see, a key point. Now we ask ourselves, what happens if we increase the amount of carbon dioxide in the atmosphere? If we add extra carbon dioxide, increase the concentration, what actually happens? Well, a man called Tyndall, John Tyndall, in 1860, made laboratory observations of exactly this. This diagram shows his a schematic of his apparatus. So he sent infrared radiation from the right-hand end through a tube filled with gas and detected the infrared coming out the other end on the left. What he found was that the effect of each additional gas molecule reduced. As the concentration of gas increased, the marginal effect, the additional effect of each extra molecule was smaller and smaller. This was referred to as saturation. What's happening is that as the infrared radiation passes through the tube, it gets less and less. And if the concentration is high enough, there's very little radiation left at the end of the tube. So it doesn't matter how much extra gas you put in, there's no radiation left anyway. So this is what we call saturation. And here we see some of Tyndall's measurements from 1860. Along the bottom, we have the concentration of gas. In this case, it's ethylene, but it applies to most gases. So we go from 0 to 25, increasing concentration, and from top to bottom, we see the amount of absorption. We can see that at low concentrations, the additional effect is quite big, but as the concentration increases, the curve gets flatter and flatter. The additional effect of each molecule is smaller and smaller. We're getting saturation. So, if the effect of carbon dioxide in the atmosphere of Earth is saturated, then what's going on? How do we get additional warming when the concentration of carbon dioxide increases if it's already saturated? This is what we need to look at. Now, there's a couple of basic things we need to go into before we can address that issue. The first one is that of black body radiation. Since the mid-19th century, we've known that bodies emit radiation dependent only on their temperature. This is known as black body radiation. So in principle, a body at a specific temperature emits black body radiation of a certain type. Now we can see the effect of temperature here. There's a 3000 Kelvin curve, which is the red one, quite weak radiation. At 5000 Kelvin, we have this blue curve, much stronger radiation. Also at shorter wavelengths. At 5000 Kelvin, the radiation peaks at a shorter wavelength than at 3000. So very important, the hotter the black body, the greater the radiation, the more intense the radiation it emits. Now, the next thing we need to look at is the structure of Earth's atmosphere. This is a diagram known as the International Standard Atmosphere. It shows the change of temperature with height in the atmosphere. So vertically on the diagram, up and down, we've got the height in kilometers, 10, 20, 30 kilometers. And left to right, we've got the temperature. So down here in the lower part of the lower 10 kilometers, this is known as the troposphere. Here at the surface, we have a temperature of nominally 15 degrees Celsius. This is just a model, an average of the Earth's atmosphere, used for purposes like civil aviation. And as we go up in the atmosphere, the temperature drops. This is known as the lapse rate, temperature falling with altitude. That's what happens in the troposphere. High altitude, colder. Above the troposphere, we have the stratosphere. That's this area here. Now, in the stratosphere, it's different. We either have constant or rising temperature. So what this means is when we combine these two factors, the relationship between radiation intensity and temperature, and the fact that in the Earth's atmosphere it's colder at high levels, this means that at high levels in the atmosphere, the infrared radiation to space is weaker. This is the crucial point. This is what causes the enhanced greenhouse effect. A man called Guy Callendar, 1938, wrote, "The change of sky radiation with carbon dioxide depends largely on this change in the altitude of the radiation focus, because the present quantity in the atmosphere can absorb nearly the maximum of which this gas is capable." So what Callendar is saying is that in the current state of the Earth's atmosphere, the carbon dioxide is absorbing as much as it can. It's pretty well saturated. But the level at which it is radiating to space, the radiating level, changes with the concentration. The level radiating out to space rises slightly as the concentration of carbon dioxide increases. This is the key factor. Another researcher, Manabe, in 1967, said the same thing. Given a vertical distribution of relative humidity, the warmer the atmospheric temperature, the higher the effective source of outgoing long-wave radiation. Manabe refers to the effective source, but it's the same thing. So it's the level in the atmosphere where the radiation is emitted from that's critical. The higher that is in the atmosphere, the colder it is, the weaker it is. So the warming effect of CO2 is indirect. It's the rise in the radiating level to higher, cooler regions in the atmosphere with weaker infrared radiation to space that causes the warming, that causes the imbalance between incoming and outgoing radiation. Now, we saw earlier that in the stratosphere, temperature rises with altitude. So maybe it should be the opposite in there. Maybe increasing concentration could cause cooling, and it does. We find that in the stratosphere, and this was pointed out by Manabe, in the stratosphere, as CO2 concentration increases, we actually get cooling. You can read more about this in my book, Freed from the Iron Grip of Frost.